So we've seen linear motion, we've seen rotational motion. Now we're going to look at combination motion. And all that is an object that rotates as it moves along a trajectory. So it's an object that is rotating but also moving linearly as well. And whenever you're converting linear to rotational, or I should say linking rather than converting, radius is the key to linking the two. And we're going to use three simple translations, I guess would be the best word. To go from distance linearly to theta, you're going to take the radius times theta. So you can do the same thing with displacement. So delta x equals the radius times the angular displacement. To go from velocity, you're going to take the radius times the angular velocity, and linear acceleration is equal to the radius times angular acceleration. So, to go from linear to rotational, all you're doing is taking the rotational value and multiplying by the radius. Vice versa, I don't think I need to write this, but theta would equal x over the radius, omega equals v over the radius, and alpha equals a over the radius. So the link between linear and rotational motion is radius. Every point on a rotating body is going to have the same angular velocity. However, 2 points at different distances from the axis of rotation will have different linear velocities. So what does that mean? Say you have a circle. Think of a merry-go-round or a carousel. So say you are standing here. Here's the center. So this would be your radius. And say somebody else is standing here. So that would be their radius. You're going to have the same omega because your angular position is changing at the same rate. However, you're going to have different v. And remember, v equals r omega. So the larger your radius, the larger your linear speed. So someone who's on the edge is going to have a larger linear speed. You're going to be going faster. Think of it this way, you're going to have more distance to cover in the same amount of time, so therefore you're going to have to be going faster. So this is again important that you recognize they're going to have the same angular velocity but different linear velocities. Okay, so I'm going to do 3 examples again, dealing with this linear to rotational link. If you feel okay after the first one, then feel free to stop. They are 3 different examples, but they're doing the same basic thing. So feel free to keep watching all 3, but if you feel okay after the first one, then go ahead and stop. Okay, so first one. A car accelerates from rest to a speed of 16 meters per second over a distance of 20 meters. The tires on the car have a radius of 0.3 meters. We want to know what is the angular acceleration of the tires, and we're going to assume that these tires aren't slipping. So they're just doing full rotations, no sliding. Given. It starts from rest, so V initial is 0 meters per second. V final is 16 meters per second. And delta x is 20 meters. Tells us the radius of the tires, 0.3 meters. And we are looking for angular acceleration. There's 2 ways to solve this problem. You can convert everything in the beginning or you can convert at the end. It really doesn't matter. You'll get the same answer either way. I'm going to make life easy and just convert at the end. So figure out what the acceleration is. We're not given time. We don't need it. Let's use the no time equation. V final squared equals V initial squared plus 2a delta x. So V final squared over 2 delta x equals a. 16 meters per second squared over 2 times 20 meters equals acceleration. So 16 squared divided by 40 equals 6.4 meters per second squared. And that's my linear acceleration. We know that linear acceleration equals r alpha. So angular acceleration equals linear acceleration over radius. 6.4 meters per second squared divided by 0.3 meters equals alpha. This is going to give us 21.3, keeps on going, radians per second squared. So my alpha is about equal to 20 radians per second squared. I could have easily solved the problem by converting velocity and displacement into angular velocity and angular displacement. I would have ended up with the same exact answer. So there's no real right or wrong way as to what order you want to do this, just as long as you are making sure to do the conversion it's asking for. Okay, next problem. Example if you feel like doing this one. We have a carousel that slows down from a rate of 6 radians per second to 3 radians per second over the course of 4 seconds. Part A says, what is the angular acceleration of the carousel? Part B, linear acceleration of a person 2.5 meters from the center. And part C, the linear acceleration of someone 1.2 meters from the center. So remember, someone who's farther from the center is going to be moving faster, so therefore they're going to have a greater acceleration. So our answer for part B should be greater than our answer to part C. So let's start with our given. It tells us that the initial angular velocity is 6 radians per second. Final angular velocity is 3 radians per second. And the time is 4 seconds. We are looking for angular acceleration. And then when the radius, call that radius 1, equals 2.5 meters, we want the linear acceleration. And for the second radius of 1.2 meters, we want that acceleration as well, linearly. So we'll start with the easy one. Part A, angular acceleration is omega final minus omega initial over time. 3 radians per second minus 6 radians per second over 4 seconds. So 3 minus 6 is negative 3 divided by 4. This is negative 0.75 radians per second squared. I didn't draw a diagram, but because this is negative, we're going to assume that this is a carousel slowing down in the counterclockwise direction. Remember, negative angular acceleration means that it is slowing down counterclockwise or speeding up clockwise. So part A, we have our angular acceleration. Let's look at now part B. Tangential acceleration equals the radius times the angular acceleration. So this is just going to be 2.5 meters times my answer from part A, negative 0.75 radians per second squared. This equals, so 2.5 times negative 0.75, negative 1.875 meters per second squared. So for the person on the end, their acceleration is about negative 2 meters per second squared. I didn't round this. The first one should be about negative 0.8 radians. per second squared. And then part C, acceleration equals the radius, 1.2 meters, times the angular acceleration, negative 0.75 radians per second squared. This equals negative 0.9 meters per second squared. So someone closer to the center of the carousel is going to have a smaller linear acceleration, even though everyone on the carousel has the same angular acceleration. That also means that this person is moving more slowly than this person. Okay, and the final example, a person pushes the edge of a merry-go-round while running around it. The person starts from rest and reaches a linear speed of 4.5 meters per second. The merry-go-round has a radius of 2 meters, and the person runs around the merry-go-round 2 times while accelerating. First, what is the angular acceleration? Second, what is the linear acceleration of the person? So again, let's list our given and find. We know that initial velocity of the person is 0 meters per second. Final velocity is 4.5 meters per second. Radius of the merry-go-round is 2 meters. And it tells us that they go around 2 times while accelerating. So that means your delta theta, we are looking for angular acceleration and linear acceleration. Okay, so let's start with the linear. There's no reason why I'm doing this first other than I'm given my linear speeds and this is an easy conversion. So we know that delta x equals r delta theta. So that equals 2 meters times 4 pi radians, or 8 pi meters. No time, we don't need it, so let's use the no time equation. V final squared equals V initial squared plus 2a delta x. V initial goes to 0. V final squared over 2 delta x equals a. 4.5 meters per second squared over 2 times 8 pi meters equals a. And this will come out to 0.402, keeps on going, meters per second squared. So my linear acceleration, again I solved part B first, is about equal to 0.4 meters per second squared. Part B, looking for my angular acceleration. A equals r alpha, so a over r equals alpha. My unrounded 0.402 keeps on going. Meters per second squared divided by 2 meters equals alpha. Dividing that out, we get 0.201, keeps on going, radians per second squared. So angular acceleration is about equal to 0.2 radians per second squared. Not terribly complicated. This is harder than just the plain kinematics because you are dealing with objects that are rotating and moving linearly, but I wouldn't consider this terribly hard. So we'll do more practice in class with this, and then we'll move on to dynamics.